let's make a start then. So firstly, did anyone manage to find a solution to either of these problems? So just starting with the top one, x squared plus y squared equals z squared. Anyone find any integer solutions there? So just want to pop them in the chat. Yep, the most common one I'm sure you likely think of is Pythagorean triplet of 3, 4, and 5. You could, of course, have like 5, 12, 13. You could have any multiple of 3, 4, and 5, or 5, 12, and 13. 7, 24, and 25 is another one, and say various multiples of those numbers. So it's easy enough to find solutions when n equals 2. But what about when n is greater than 3? This suddenly becomes a lot harder to solve. So I won't make you kind of have any longer on this, because it does actually turn out there are no solutions to this. Okay, now I'll put a little clip from The Simpsons there in the bottom left. Now that solution, if you put in your calculators, it appears to work, and it does work to 10 significant figures, but it doesn't hold to greater accuracy. So it looks like we get close with that solution that's there in the bottom left, but we don't actually quite get there. So this problem is Fermat's last theorem. Fermat's last theorem states that there are no integer solutions for where n is greater than 2. Okay, so there's no solution to that for where n is greater than 2. And this problem was, well, in the 17th century, his son claimed that Pierre de Fermat, French mathematician, had proven this problem, but that the proof was too big to fit inside the margins. Okay, so that seems like a pretty convenient excuse. Oh, I can't print my very long proof here. Now, this was the 17th century, where proofs were often kept very secretive and generally not shared. And his son went to publish that he'd proven this, but this was after Pierre de Fermat's death. So what this led is mathematicians on an over 350-year journey, which tormented many mathematicians and drove, I think, some of them actually quite close to insanity, trying to prove this problem. It took them over 350 years before we fast forward to 1994, where British mathematician Andrew Wiles finally proved this after this problem being about for over 350 years. Along the way, it led to many mathematical discoveries, and is often regarded as one of the hardest problems in maths due to many people having unsuccessful attempts. This is probably due to the fact that the problem's quite easy enough to understand, but the proof of it is very complex. Okay, I'm not going to go through the proof of this because it has some very high level maths that you wouldn't have studied yet, but just know it is quite complicated. So what we're focusing on today is proof. But before we get into the different types of proof that we have, firstly, I want to talk about different types of numbers and a little bit of notation. So you will have seen some of these different notations as you go along, but it's really important to be clear on them because we're going to be using them throughout this whole booklet. Now, firstly, in terms of what types of number there are, firstly, we have the natural numbers. So what I'm drawing here is just a slight different take on how it's been drawn in your booklets. This is just on page 2 in your booklet, if you want to have a look at a different diagram on this. So firstly, we start off with the natural numbers. So these are just our counting numbers. So anything like 1, 2, 3, 4, 5, 6, also including 0. So we can have 0, we have 3 in there, 8 in there, 1 in there. All of those are our natural numbers. So if you see this n, it's probably better to look at this bit here where I've highlighted. If you look at n there, so if you see an n drawn like that, it's referring to the set of natural numbers. Next up, we have integers. Okay, so natural numbers are integers. Integers are just positive or negative whole numbers and also include 0 as well. So all the natural numbers are integers, but also integers allows us to include things such as -5. 5 minus 13 minus 289. Okay, as well as including all the natural numbers as well. So a natural number is an integer, but an integer is not necessarily a natural number. Hopefully that makes sense in terms of the sets that we have here. So if you've got any questions, just make sure you do pop in the chat as we go along. So the integers we denote with this Z here. Then we have our rational numbers, or sometimes they're referred to as quotients, which is why we use a Q here. Now the rational numbers, these are any numbers that can be written as fractions. So yet again, this will include your natural numbers because, for example, the number 8 can just be written as 8/1. Okay, but these this A and B, both of these have to be integers. Okay, so A and B both have to be integers as we're writing these rational numbers. So this includes things such as things like a third. Okay, now that's obviously not an integer. Okay, but you can write it as one integer over the other. So that's a quotient or a rational number. Okay, and yet again, all the integers are rational numbers, all the natural numbers are rational numbers as well. This will also include things such as 1.3 reoccurring, for example, because I could just write that as a much simpler number as 4/3. So I can write it as a fraction. Then the next thing we have is the real numbers. So I know people have come across a lot of questions before, as you can see here right at the bottom, where it might say X and then this kind of E-like symbol and then this R here. What this means is that X belongs to the set of real numbers. So it basically just means X is any real number. So it's anything really that we would define as a number. So that, yet again, includes all the natural numbers, all the integers, all the quotients, or all the rational numbers, and also the real numbers will include irrational numbers as well. So an example of an irrational number, probably the most famous one, is pi. Pi cannot be written as a fraction, so it's not a rational number, it's an irrational number. Okay, so rational numbers can be written as fractions, irrational numbers cannot be written as fractions. So this includes pi, also the exponential function e, and also would include your surd, so things like square root of 2, the square root of 3, and so on. Okay, all those numbers there cannot be written as fractions. Finally, we have the complex numbers. Now, don't worry too much about these ones. This is only really applicable if you do further maths. Okay, this includes I, which is the square root of -1. In A-level maths, we don't need to worry about any of that. So really, complex numbers, that's only there for the further mathematicians. Okay, but what you do need to know is if you see the N, it's the natural numbers. So 0, 1, 2, 3, 4, 5. Z is the integers, so positive and negative whole numbers, including 0. You've got the quotients or the rational numbers. So anything could be written as a fraction. And then finally, everything else just comes under real numbers, as long as you're not including the complex numbers, so the square root of negative numbers. Okay, so really, if you just see X is any real number, basically just think of any number that's not the square root of a negative number. Okay, that is a what we refer to as a real number. So now we have notation, we can talk about why we want to prove statements. So this isn't this bit here isn't actually in your text in your booklets. It's just a bit of extra stuff I wanted to include here. So why is proof important? So let's say when we do a hypothesis test, so taking us back to when we've done statistics, we may use a significance level of, let's say, 5%. What this means is we may end up rejecting the null hypothesis, but that doesn't mean it's always correct to do so. So we might do an experiment and we might find that our probability from our sample was less than 5%, and we end up rejecting the null hypothesis and we accept an alternative hypothesis. Now, a significance level of 5% means that 5% of the time we're going to be incorrect to reject the null hypothesis. Alternatively, we could say that we're 95% sure that we are correct in rejecting the null hypothesis. Okay. One key thing here I will say in terms of the test that you just done on a question that quite a few marks were dropped on, that fact there of what a significance level is going to be quite important to that test that you did the other week. So a significance level of 5% means that 5% of the time we are incorrect to reject the null hypothesis. So like I said there, 95% of the time we're confident, but we're never 100% accurate with a hypothesis test. And you'll find that in science, many theories are often formed, but often is the case that theories are later disproven. Very rarely are we ever 100% sure in an experiment. We can be quite confident, but rarely are we ever 100% sure. In maths, when we construct a proof, we want to be 100% certain. Okay, there's no subjective, there's no argument here. You can't say that Pythagoras' theorem is fake news. Okay, you are 100% sure that that proof is correct because there's logical steps that hold true, and it will show that it works all of the time. When we do a proof, we can't just assume that it works just because it works for one set of numbers. It'll work for all sets of numbers. Okay, it's important that when we are proving, we prove theorems because we want to make sure that other mathematical proofs hold true, and also other discoveries may be made based on the proofs that we find. When we construct a proof, so getting now into when we are getting into our exam, when we're constructing a proof, it's important to make sure that steps are clear and it's easy to follow the proof. Okay, we always want to start from the beginning and end up with the final statement. I put it here in bold because it is very important. Always include a conclusion at the end when you do your proof. So you might think, well, why do we prove? There's some of the reasons I gave there, that it gives us, it helps us make sure other proofs are true and may even help make further discoveries. Also, a lot of mathematicians do just find this really enjoyable, and the whole problem solving of all. There's also a lot of money in proofs here. So these are the Millennium problems that if you solve any of them, you'll get $1 million for doing so. For example, the P versus NP problem. If you do computer science, or if you do further maths and do decision maths, you might want to have a look at that one, because some of these are quite difficult to understand what it's actually asking you to prove, but you might enjoy reading up on that if you're doing computer science. So getting into what we might have to do in the exam. So I know I've talked a bit there, but it's important that we've got the right notation and we understand why it is important that we are proving. Just before I continue, we'll just double check in case any questions. Nope. So there's 4 different types of proof that we're going to learn in this booklet. The 2 that we're going to focus on today are proof by counterexample and proof by exhaustion. Over the week, we'll look at proof by deduction and proof by contradiction. The first proof that we're going to look at is proof by counterexample. Now, all these proofs, by the way, it's not that these are the only proofs. There are other proofs as well. If you do further maths, you may have come across proof by induction as well. But starting with our first proof, proof by counterexample, basically what we're going to do here is we're going to find an example where it doesn't work. Okay, so that's what a counterexample is. So if something is said to always be true, if we're trying to prove that that's not the case, we just need to find one value where it doesn't hold up for. If you're claiming something is always true, it has to work for every single number. If you can find one example where it doesn't work, then that proof is not correct. So our example here, this is the one in your booklet on page 4. David says that x plus 5 all squared is equivalent to x squared plus 25. By the way, these 3 lines here means equivalent, okay? And basically this isn't an equation that you solve, this is an identity. Okay, so if you see these 3 lines here, it's because it's an identity, and it means that the left-hand side always equals the right-hand side. So we're going to prove this by a counterexample. So all I need to do here is pick a number and then show that this doesn't balance. So I'm going to just say let x equal 2. And what I'm going to do first is look at what happens on the left-hand side. You might see me quite a lot in this chapter put LHS and RHS, that just stands for left-hand side and right-hand side. So on the left-hand side, I do x plus 5 and then square it. That gives me 49. On the right-hand side, I do 2 squared plus 25, and that equals 29. So what we've found here is the left-hand side does not equal the right-hand side. So the statement here was it works for all values of x. I don't care if it works for every single other number except for 2. Okay, it doesn't, by the way. This only works for 0. But even if it worked for every single number other than 2, you still can't say it works for all values because it fails on the x equals 2. So then we make our conclusions. We say David is wrong. X plus 5 all squared does not equal x squared plus 25 for all values of x. Okay, it might seem tedious to write your conclusions at the end, but I will be deducting marks when you do assessments, as the examiners will if you don't put that conclusion at the end. Okay, the number of times people do the proof perfectly, but then they don't finish it off with that conclusion, so they lose that final mark. Okay, don't lose that final mark in the exam. Anyone got any questions so far? Note that I did this, by the way, for x equals 2. You could also do this for x equals 3, x equals 4. You could try any other numbers here and you'll still find that it works. So that's an example of proof by counterexample. Basically, just find an example where it doesn't work. That's what you want to do for a counterexample. Proof by exhaustion is kind of as it suggests. We're going to exhaust all the possibilities. Okay, so it might seem like it's quite tedious. So try and think about exhaustion. You're going to be having to exhaust all the possibilities. Now, it's not always practical to do that. For example, if you're proving for all values of x that a statement is true, then you can't just prove for all infinity. This will basically be useful for where we just only have certain numbers to look at. In the next lesson, I'm going to show you where we can also use proof by exhaustion, but we are proving for all values, but there's ways that we can take shortcuts to group certain numbers together. Okay, but for today, just going to keep it nice and simple with a question like this. So we're going to prove that y squared plus 1 is not divisible by 3, where y is an integer such that it's between y is between 6 and 10. Okay, so it's an integer, so I only need to test 6, 7, 8, 9, and 10 here. So I'm going to start off with y equals 6. Well, I do 6 squared plus 1, which gives me 37. 37 divided by 3 is 12, remainder 1. Okay, so not divisible by 3. Then I try y equals 7. So 7 squared plus 1 is 50. 50 is not divisible by 3. Just putting a ditto there. And you can see why it's proof by exhaustion, because it is a little bit, it can be a little bit tedious for questions like this. As I said, we'll look at some problems that are a little bit more interesting than this with exhaustion tomorrow. It's not always just going to be subbing all the numbers. There are ways we can take shortcuts for particular questions. It might not be necessary to actually show the result of dividing by 3 every time, but as I say, we want to try and show as many steps as possible with a proof. So here we can see that every time I put in a value of y divided by 3, I'm always getting a remainder. So therefore, we're not done yet because we have to make a conclusion. We'd say y squared plus 1 is not divisible by 3. When y is between 6 and 10. Okay, so just making that conclusion at the end. So to recap the 2 proofs that we've learned about, proof by counterexample, find a situation where it doesn't work, proof by exhaustion, just prove it for all the numbers within a given range. So something a little bit different I'm going to do today. Just as a review, what I want you to do is just give you a few minutes and I'll go through the answers to this. So I've just kind of put up some quick questions here. So I'll give you a few minutes, just have a go, and then I'll come up with the answer. So I'm getting you to do something now. So just a little review. I want you to write down an irrational number. I want you to write down a number that is a rational number or quotient, but it's not an integer. And then question 3, Johnny says that sine theta plus sine A is equivalent to sine theta plus A, where theta and A are angles in degrees. Prove that Johnny is incorrect in saying that. And then 4 says prove the probability of getting X number of tails when you flip a coin 3 times is always less than 0.5. So I'll give you about 3 or 4 minutes to have a go at those, and then we'll discuss the answers to them. So just hopefully you've got a piece of paper handy, and then we'll go through some of these answers in a second. If you've got questions, just pop them in the chat. If you're watching this video back later, you might just want to obviously fast forward a couple of minutes, because there'll be a bit of silence. Yeah, okay. In the third example, so when we prove, by the way, it's not always going to be you have to use these 2 techniques. There are other ways to do it. Yes, you can expand the right-hand side. However, unless you've read ahead into what we're going to do in second year, I don't think you'll know how to expand that right-hand side just yet. So in terms of how we expand that right-hand side, we look at that in second year when we do trig. If you have got the formula booklet, you might be able to spot what actually happens there and why it's not true. But for now, I'd recommend just the proof by counterexample to do that question 3. I'll give you 1 more minute and then we'll go through some answers there. If 1 minute's not enough, you want a bit longer, do put something in the chat to say you want a little bit longer. If not, I'll give you another minute and then we'll go through some answers. Right, okay, so firstly what I want to do is for the first question, if you want to just start writing in chat, just write down some examples of irrational numbers. Obviously, some of them you might need to kind of write in words instead. So obviously there's no kind of maths function for the chat. But just firstly, question 1, give me some examples of some irrational numbers, maybe ones that I didn't mention earlier. Okay, so we've got people saying square root 2e, yeah. Now we could actually get even more creative. We could even say things like square root of 6 plus 1. Okay, that would still be an irrational number. Just because 1 isn't an irrational number, just because 1 is a rational number, doesn't mean that when we do root 6 plus 1 that we it becomes a rational number. We could also even do things such as e squared and things like that, or even make it 3e squared or something like that. Okay, and yet again we could have like 6 pi as well as just having pi. Okay, and then a rational number or quotient that's not an integer, so that could be anything that's a fraction that you can't write. There can't be an integer. So you've got something like 3 over 4, you could have minus 5 over 7 for that one. For 3 then, can anyone give me, so I did mention earlier that we'd need a counter example. So for question 3, can you give me a value of theta and a where this doesn't work? And then we'll test it out. So 45 and 15. Okay, thank you. There was that. That's Zach. Okay, thank you. So we've got theta as 45 and a as 15. So on the left-hand side, we'd do sine 45 plus sine 15. Put that in your calculator and you will get root 6 plus root 2 over 4. The right-hand side, well, that just gives us sine 60, which we should just know as root 3 over 2. Okay, now clearly the left-hand side does not equal the right-hand side. If you weren't sure with your search, you could always change in decimals as well. So then we'd make a conclusion that Johnny is wrong. Sine theta plus sine a does not equal sine theta, or does not always equal sine theta plus a. Okay, if you made theta and a 0, it would work, but there's very few cases where this does work. In terms of what sine theta plus alpha in a bracket is, you'll find that out in second year when you do trigonometry. And then finally, this kind of goes into a bit of probability. This would be a proof by exhaustion. We would say that we've got x here. Just draw out the table. And we could just show all the probabilities. So we get an eighth, 3/8, and then finally an eighth. Okay, this is just from Pascal's triangle because the probability of a head or tail is 50%. So you just get 1, 3, 3, 1, the third row of Pascal's triangle here. But you could work this out with binomial distribution. And then we can just see that for all values that we put in, they're all less than a half. So therefore, the probability is less than 0.5. I'm not doing it here just because of time's sake, but just make sure that you do always put conclusions there. So I hope that's nice and clear. If you do have questions, please let us know. So now you can do all the questions that are attached to assignment. So there's a sheet of different statements to prove. Don't just do the ones that we want to take, want you to take photos of. Do have a go at all of them because there's many different styles of proof. And once you kind of know the key to a particular type of proof, then it does kind of help you with other questions. So once you've kind of done it once, you'll see another question later on that could be one in your exam, and then you'll know how to prove it. So the ones that we want you to take the photos of are there. And there's solutions available to all the questions except for the ones that you're going to hand in to be marked. Okay, so make sure that you do go through those proofs and ask us questions if you're not sure. If you just, or maybe it might just be that you need a hint. If there's any more questions, I'll take them now. Otherwise, that will be the end of today. And we'll see you tomorrow for some further, we'll do some further exhaustion problems. And we'll also look at proof by deduction as well.